The broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone, to Understanding Camera Resolution, a webinar hosted by Photonics Media and sponsored by Midwest Optical Systems. My name is Robin Riley, and I am the Photonics Media web editor. Our speaker today is Daniel Olache, Product Marketing Manager at Baumer. Daniel will be speaking with you today on what you need to know about camera resolution in order to achieve the best results under a wide range of conditions. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. If you would like a hard copy of this presentation, please send me an email after the webinar. We encourage you to ask questions throughout Daniel's presentation. Please type your question in the question box to the right of your screen. We will answer as many as possible at the end of the session. And with that, I would like to turn the presentation over to our presenter, Daniel Olache. Welcome, Daniel. Okay, Daniel, I don't hear you. I don't see your microphone on, but I do see your screen. You just might have to hit your microphone button to make sure that you're on. Okay, I still don't hear you.
Hi, hello, can you hear me?
Yes, you're coming in loud and clear.
Awesome.
Okay, thanks.
Sorry, I'm not sure what was going on there. Thank you, Robin. Hopefully everyone can see my screen. Like Robin said, my name is Daniel Olache. I work for Baumer. I'm the product marketing manager for the vision component of Baumer. And today we're going to be talking about a camera resolution, understanding what it is, how much you need, being able to calculate how much you need, and then also understanding the different factors that go into, you know, how much resolution you need, like lighting, lensing, software, and things like that. So we're going to go to the next slide here. This is the outline. We're going to start out with a simple formula that you can start with, and then we're going to discuss how other factors such as lighting, lensing, 2D camera calibration, part placement, and software can affect the resolution of your camera beyond, the megapixel value of your camera. And then we're going to go over the conclusions, and then any questions that you might have, we'll try to answer those at the end. Okay, so a starting point to selecting the resolution of your camera. So just simplistically, as an overview, each digital camera has a sensor built into it. And this sensor is composed of a grid of pixels in the X and Y direction. And the number of those pixels determine the megapixel rating of the camera. So a megapixel, just 1 megapixel, is 1 million pixels. And you can see here, as an example, we're using a VGA sensor as an example. That's 640 by 480 pixels. And another thing to notice here is a lot of these sensors, they're not square, they're actually rectangular, which comes into play which way you orient the camera. So you want to make sure that, if your application requires, more pixels in one direction, that you orient your camera that way. But for this example, the VGA sensor has 640 by 480 pixels. You multiply those two numbers together to get the whole number of pixels in the area of the sensor. That's 300,000-ish pixels, and that's considered a 0.3 megapixel sensor. And that's how you get the ratings for cameras. So you see, 20 megapixel camera, that's going to be 20 million pixels. So down here at the bottom of the screen, you're going to see a formula. And this is what I mean by a starting point for selecting the resolution of your camera. And the formula is number of pixels needed equals field of view, FOV means field of view, multiplied by the accuracy divided by the tolerance. And we'll go through what these different terms mean in the next slide here. So again, number of pixels equals field of view times the accuracy divided by tolerance. So the number of pixels needed, that's the resolution you need. Field of view, that's the area that your camera is going to see. So if that's 10 inches by 10 inches, that's your field of view. Tolerance, that's the smallest detail that you need to see. Or for measuring applications, that's plus minus 0.01 inch, for example. That's your tolerance. Your accuracy is actually contingent on the software that you're using, as well as depends on the application. So for certain applications, such as measuring applications, software can actually be sub-pixel accurate, which means that the software can actually estimate between pixels where the edge of an object is based on the gradient as an object gets darker or lighter over multiple pixels. We'll look at what that looks like in the software section of our slides in a little bit. So as an example of this equation in action, let's say, for example, we wanted to take a look at a 10 by 10 inch area, and we wanted to measure a tolerance of 0.01 inches. It's pretty small, but the field of view itself is pretty small as well. And let's say the software we're using is accurate to 1/4 of a pixel, and we're measuring, an object. Thus, we have 250 pixels as the number of pixels needed based on this equation. 10 inches as the length multiplied by 0.25 divided by 0.01 inches. So a standard VGA camera, which again was 640 by 480 pixels, would be able to do the job in this case. So it's important to remember that this equation is just a starting point. It's not that easy. If it was that easy, we could just stop the presentation here, but there's a whole bunch of other factors that influence resolution and the amount of resolution you need. So in the real world, lighting is never perfect. Items are not perfectly thin. Items can't be placed directly under the camera, so they're moving around on a conveyor belt or what have you. You can't buy the perfect lens, so lenses always have imperfections, distortions, things like that can affect how much resolution you need. And like I said, objects might be moving. Software is different for different applications. We'll take a look at all these different factors and see how they affect the resolution of your system. So lighting. Lighting is a crucial part of any machine vision system. You use lighting for all machine vision applications. Sometimes that lighting is built into, let's say, a smart camera. Other times it's an external light. And we'll go over a couple of the common light forms over the next couple of slides. So a very common type of light is called a backlight. Backlights are used typically in measuring applications. So you have a light underneath or behind the object. You have the object in the middle, and you can kind of see this on the lower left of the slide. So you have the illumination, the light behind the object in the middle, and then the camera on the other side. And what this does is it creates a very nice silhouette of the object with nice crisp lines, and you can do a lot of measuring or checking for patterns that way. And this is what a backlit image would look like in the real world. And this was actually an application we did where we were trying to measure the gap of this ring. So we'd have a backlight behind the ring. The ring is in between the camera and the backlight. And then we were able to, identify where this gap is and then measure the gap. If it's too big, you'd want to reject that. If it's too small, you'd want to reject it. If it's, the right size, then you can let it pass. So as you can see, it creates a really nice, crisp image, nice edges. So it's very easy to measure the distance there. So front lighting, it's light that comes from the front, so the same side as the camera. It bounces off the object, and then the light bounces back, or the whole image bounces back into the camera. I'll show you what that looks like here. So front lit image, counting bottles. This was an application where you didn't want a silhouette. You wanted the caps of these bottles to really pop very bright to count them. So if there were 5 or 4 bottles, you'd want to reject that that product. If there were 6, and you could count them based on the brightness of the cap, then you'd want to pass that product. So of course, there's a whole bunch of different lighting options. I'm not going to go through all of them. There's front lighting, back lighting, dome lighting, spot lighting, dark field lighting. And here in this graph, you can see what those different lights look like on, an object of 10 cents or 10 euros. But for each application, of course, it's different, and you're going to have to play around with the lighting based on what you're trying to do. Just briefly, I'm going to go over filters. There's a whole bunch of different filters out there. The one that we typically use with front lighting is a polarizing filter because it reduces the glare that bounces off an object. In this case, you can see you're looking at a 2D code and a barcode. And on the left, you can see without a polarizing filter, you can see there's a lot of glare. And you can imagine that that would create some issues if you're trying to read that barcode and that glare was right on top of it. And then on the right, you can see that that's with a polarizing filter. It really reduces glare. So in summary, lighting is integral to machine vision. It's often trial and error. Of course, as you do it, you get better at figuring out, for this type of application, this light typically works. But as far as like angles and distances away from the object and away from the camera, that's really where a machine vision lab comes in handy. So you have different types of lights, and you just have to test it to make sure that your image quality is as good as it can get. Because if your lighting isn't great, it will reduce the image quality, and you might have to go up in resolution to identify the same features, whereas a better light might be able to fix that without having to do that. Lenses. Lenses are the next topic we're going to cover. So lenses all are rated for a specific type of resolution as well. And as where cameras, you have the sensor inside the camera that determines how much resolution that camera is rated for. So a 20 megapixel camera will have a 20 megapixel sensor built in. Lenses aren't like that. The rating that they have is based on the quality of lens and the quality of the manufacturing process that they're created with. So a 10 megapixel lens will be higher quality than a 2 megapixel lens. It just means that they were created with tighter tolerances. And this is really important because if you have a high resolution camera, so let's say you have a 20 megapixel camera, and you're using a 2 megapixel lens, your image is going to be greatly reduced in resolution because the image is passing through that lens. So it's important to use a lens that fits at least the resolution of your camera. So if you're using a 20 megapixel camera, make sure that you're using a 20 megapixel lens or higher. Of course, as you go higher, the lenses get more expensive. So typically you would want to use a 20 megapixel lens or something close to that, but at least 20 megapixel for a 20 megapixel camera. Field of view, this is important because the larger your field of view, the lower your pixel density. So if you're looking at a big area and you're looking for small details, you're going to need a much higher resolution camera than if you're looking at a small area and looking for those same details. And the lens comes into play here because a bigger lens, let's say a 35 millimeter or a 50 millimeter lens, is going to be more zoomed in on your object than, let's say, a wide angle lens like an 8 millimeter lens. And I have an example of that on the next slide. So always strive to keep the smallest field of view possible. Of course, objects in the real world move around. So let's say you're looking at a bottling application. Your bottle is not going to be placed on the conveyor belt perfectly in the same spot every time. It might, have a tolerance of plus or minus an inch in the X and Y direction. And that's important to know what that is so that you adjust your field of view accordingly, so that you're not, zoomed way out, and then you're not going to be able to see the details of the bottle as well as if you were, had a better cropped image. So in this example, you can see what I was talking about. The 8 millimeter lens, same camera, same distance away from the object. On the left here, you have an 8 millimeter lens looking at a hotel card key. And it's zoomed out pretty far. You can see the whole key. And on the right there, it's a little bit out of focus, but 35 millimeter lens, you can see that the image is much closer. And in both these images, you have the same exact amount of pixel density. So let's say the letter I there has maybe 50 pixels, is 50 pixels wide on the right, and on the left there, maybe it's only 5 pixels wide. You can see how that plays into, locating defects in products or things like that. So it's really important that you try to make your field of view as small as possible for your application. Okay, moving on to 2D camera calibration. And this is important because lots of times we're measuring products in the real world, and similar to the way our eye works, cameras will see an object that's far away as smaller than an object that's close. So objects that are closer look bigger to the camera, and objects that are farther away look smaller. This is an illusion called projection. Our human eyes do this, so we know what this feels like. And that's why we need to do 2D camera calibration, which allows us to convert pixels to real-world coordinates, such as inches or millimeters. So how this works is you have a graph. Sometimes they're clear, nice graphs like this. In these images, you place it directly on top of your product, and then you're able to, with software, correlate pixels to inches or millimeters. So it's really important that you place this graph at the exact same distance away from the camera as the part that you're trying to measure, because of this illusion. Because if you place it further or closer, you're not going to measure the pixel to millimeter or pixel to inches will be off. And then it's also important that product placement after calibration is very spot on, so your object isn't moving closer and further as you're inspecting them, because then you'll be off as well. So there is something called a telecentric lens, which is really cool because it lets you see an object no matter how far away it is, it looks the same size. So there's some benefits to this for sure in measuring applications. Here on the bottom right, you can see what an endocentric lens is. That's kind of what our eyes do. Further away objects are smaller, and typical machine vision lenses are endocentric lenses, and then the specialty telecentric lenses are great because you can measure an object even if it's further away, as long as it's in focus, of course. It's not going to look bigger or smaller to the camera, no matter how far away it is. The downsides to the telecentric lenses are they're expensive, and the lens needs to be much bigger because your field of view can only be as big as the width of the lens, and that's really a limiting factor for a lot of applications. So here on the top left here, an interesting illustration of what that looks like to the camera. An endocentric lens would see what's on the right here. So those circles wouldn't be, perfect circles depending on how thick that piece is. But on the left there, that's what a telecentric lens would see. So there's definitely pros to a telecentric lens in some measuring applications. Heat and sensors. So this is important because cameras tend to get hot, especially if you're running, high resolution cameras at quick rates, so high frames per second. And the heat, if you don't have good heat sinks or heat dissipation, can actually warp or move the sensor inside the camera, and that will create some distortion within the image. It'll mess up your measuring applications, especially for very tight tolerance applications. So it's important to make sure that you're dissipating that heat that that camera is creating. Bad pixels. So every sensor, is composed of hundreds of thousands or millions of pixels. And within that sensor, there are going to be a few bad pixels. They're not in the same location every time. It's just unique to each individual sensor. And a lot of camera manufacturers correct for bad pixels via software and things like that. So it's important to understand that, these sensors do sometimes have bad pixels, especially for applications where you have extreme tolerances. You want to keep that in mind and then make sure that the software you're using eliminates those bad pixels. Lens distortion. This is another factor that can influence how much resolution you need, as well as your field of view. So within each lens, you're going to have a little bit of lens distortion, and this typically occurs on the outsides of the lens. You can see here on the top right, that was what the image should look like on the left, and those are two different types of distortion, exaggerated of course, but in the middle is where, in the middle of the field of view is where you're going to be able to measure most accurately. Towards the edges, that's where you're going to get that distortion, either concave or convex. Part placement, this is another aspect of, another thing to consider when designing a machine vision system. How is your part placed? Is it moving? Moving parts, especially the fast moving parts, can create something called pixel blur. And that's where your image is actually blurred, kind of like in sports images and things like that, where they actually do it purposefully to convey a sense of movement. Typically in machine vision applications, that's a bad thing. So you want just like a still life image, which can be difficult, especially for fast moving parts, like I said. Really the way to correct for that is to have a very high intensity light that really lights up the image very bright, and then reducing your exposure time so that the camera is only open for a couple microseconds, just really fast, and then you get a very nice crisp image. And that's something to consider with lighting, definitely, and then also the camera that you're using in terms of what the minimum exposure time is for your camera. Okay, software. So there's a whole bunch of different softwares out there. Some are sub-pixel accurate for some applications and not for others. So it's really important to understand your application and then find the software that best fits that application. So there's barcode reader softwares, there's measuring software, and some software are better at doing things than other ones. So for example, let's take a look at the sub-pixel accuracy of some softwares. So on the left here, we have a cell outlined by some software. So if we zoom in on that, you can see that, you know, there's pixelation as you zoom in, but there's a green line there that actually threads between some of the pixels, and that's what sub-pixel accuracy looks like. So by reading the values of its neighbors, you know, as it gradients from dark to light, you can actually, some softwares can actually guess where that outline actually is, knowing that the pixelation is occurring and you're not actually seeing the correct outline based on that pixelation. So some sub-pixel accuracy can go to 10 times or more. So it's really important to know what software you're using and what its capabilities are. So here are some more applications. You know, you have 2D codes, you have barcodes, and each software is going to have its minimum specs for certain applications. So for example, here on the left, we have a 2D code. The minimum thickness for a particular software could be, you know, 3 to 4 pixels for that each little dot on that 2D code. Other softwares might be a little worse, you know, and they might say we need 5 to 6 pixels. Some might be better and say, you know, we only need 2 pixels. Same thing for the barcode reading. You know, this one says 1.5 pixels for the smallest, you know, dash of that bar. And it's really important to understand your application, what the software can do, and then you can calculate what the camera resolution that you need is. Okay, now I'm going to go over a couple real-world examples of resolution and how they were solved. So in this case, we were looking for a 2D code similar to what we were looking at in the slide before. This is etched in metal. You can see it on the bottom there. So the field of view is actually pretty large compared to this chip, which is tiny, 1 inch by 1.5 inches. And the area was 6 by 6 inch area. So this chip could be anywhere within that 6 by 6 inch area. And they wanted to read, you know, this 2D barcode or 2D code. So we ended up using a 5 megapixel camera, so a little bit higher in resolution than the 2 megapixel that we had originally looked at. And that's because based on the larger field of view and based on the size of the 2D code, you needed something with higher resolution. Also went with a larger lens, a 35 millimeter, to really zoom in on that area. Another application example, in this case, we're looking at wires, bent wires, and the angle. So in this case, they're supposed to be 90 degrees. Wanted to see plus or minus 0.3 degree accuracy to measure the angle in this bent wire. So based on testing, we figured out that a 2 megapixel camera would be able to do it. We could, of course, make it much more accurate if we went up to 5 megapixel, 10 megapixel cameras, because the limiting factor wasn't the software, it was really the resolution of the camera and not being able to, you know, differentiate that line more accurately. Another example that really doesn't involve resolution, we had a customer, this is the one with the polarizing filter. looking at this 2D code, they were asking, do we need more resolution to read this code? And this really wasn't a resolution problem. This was a filtering problem. So by using the right filter, we could really maximize the resolution of the camera, and we're able to read the 2D code, the barcode, and read the numbers there as well. And the last application I wanted to run through was a bottling application, looking for the cap, make sure that you got the protective cover on there, and all that stuff. So in this case, we're using a backlight to get that silhouette of the object, and then the solution was a 0.3 megapixel camera, which is a VGA, which is the lowest resolution camera that we offer. And it really didn't need any more resolution than that, because the defects, such as missing cap or missing protective cover, were actually they were big, gross defects, so they weren't very fine details, and the software was able to pick that up. The field of view was pretty small because these bottles were placed accurately, and the pattern tool that we used was able to pick up differences between good and bad bottles. So in conclusion, it's important to remember that a camera is not a vision system by itself. It's a very important part of a vision system, but there's a whole bunch of other, factors that you need to consider. It's impossible to have a simple equation. That equation that I gave you at the beginning is a good starting point, but it's definitely not the end of the conversation. Some pros and cons of higher resolution cameras. So the higher resolution camera you have, the more margin for error you have. Because of the more pixels, you could get a crisper image. You can have a larger field of view without compromising detail. So you can read, small barcodes while also looking at a big field of view and potentially do multiple inspections with the higher resolution. But there's also some downsides. Of course, the higher resolution cameras are more expensive. Not only the camera, but then the lens that you need to purchase with the camera needs to be a higher quality lens. The PC needs to be higher or better and faster to process larger images. Larger resolution cameras are also slower because of the larger file sizes. Your frames per second, FPS, are going to be smaller or lower as well. They generate more heat, and if you're storing the images, this can cause issues as well. So these are the steps that you really should go through when looking at resolution for a camera. First, determine your application, determine the software that you'd like to use, its requirements, the specs, determine suitable lighting and lensing, and then you can select a camera based on the equation that we had, and then you're just going to test. So set up, your product, use different lensing, different lighting, calculate your field of view that you need, and generate lots of data and make sure that your system is accurate enough. That's really all I have. Thank you for your time. Any questions? My contact information is listed on this page as well.
Thank you very much, Daniel, for that informative presentation. And attendees, I just want to remind you, if you have any questions, now is the time to enter them into the question box on the panel to the right. And so I'm going to begin here, Daniel, with the first question, which is, what is the difference between CMOS and CCD sensors when it comes to resolution?
Sure. So CCD sensors have been around for a long time. That's really where the machine vision industry was, I'd say maybe 10 years ago, lots of CCD sensors. And now the big chip manufacturers are moving more towards the CMOS sensors. They're cheaper, and the quality of the CMOS sensors has gotten a lot better. to where now it rivals the CCD sensors in a lot of applications. And like I said, they're much cheaper, and that's really where the whole industry is going, is CMOS. I can just say for Baumer, all the new camera products that we're coming out with are based on the CMOS sensors. The CCD sensors, we still do have some cameras, and they do have some advantages based on certain applications. They do have their advantages, but really the industry as a whole is moving towards CMOS.
Okay, thank you. What is the effect of pixel fill factor on MTF?
Sure. So MTF is modular transfer function. It's a way of calculating there's two different ways. There's LP divided by millimeter, which is line pairs per millimeter, then MTF. MTF, you basically have a lens MTF graph and a camera MTF graph. And by multiplying those together, you get your system MTF. Basically, that tells you how much resolution basically you're losing through the lens and through the camera. And each camera and lens has its own MTF graph. And sorry, what was the question about pixel related to MTF?
Here's the question again.
Yes.
What is the effect of pixel fill factor, F-I-L-L factor, on MTF?
I'm gonna have to take a look at that one. Could the attendee please, you can email me for sure, and we can talk about that one offline.
I'll send you the attendee's email address
Yes,
as
you.
well. Next question here. What is the relation between numerical aperture and pixel?
Sure. So the numerical aperture is based on the lens that you're using, and the pixel size that you're using. So each sensor has a different size. So some of the larger megapixel cameras have a large sensor size, and the aperture of the lens has to be at least the same size as that sensor. So if your lens is too small, you're going to get vignetting on the edges of the sensor. And that, I wish I had an image of that, but I'm sure you've seen that like in old-time images where the corners are darkened. And that's what happens when the lens is too small for the sensor size that you're using. So it's really important to look at the sensor size that you're using inside your camera and make sure that your lens is larger than that sensor.
Okay, thank you. Next question. Can you describe the advantages and disadvantages of different sensor arrays?
Sure. So in terms of CCD and CMOS, so definitely with CMOS, like I went over, the CMOS sensors are cheaper. They used to be known to be lower quality, but now in recent years they've come up in quality. There still are some CCD sensors that are better than the CMOS sensors, and really for very fine applications where you're really looking at very detailed, maybe low light applications, that's when you would look at a CCD sensor, and of course you're going to pay a little bit more for it.
Okay, thank you. Next question. How do you quantify angular resolution in a 2D system?
Sure, so there are some softwares that if you're looking at if the camera is angled at the side and looking at a flat object, there's software corrections you can do to make that image that you're looking at an angle kind of a flat image to flatten it. And that's really based on software. So I know personally at Baumer, we do have a couple software tools that we recently came out with that do that exactly that. So you can tilt the camera at an angle and you can still do the 2D calibration. It just flattens the image first and then you can do that.
Okay, thank you. Do you ever run into issues with cosine error or light fall off when it comes to reflectance imaging?
I haven't personally, but if you do have an application that you're having issues with that, we can definitely take a look at that if you'd like to reach out to me.
Okay, thank you. The next question is about IR camera applications, and I guess I will ask, can you say anything about resolution for IR camera applications?
Sure. So IR, I haven't worked too much with IR cameras. So I'm not exactly sure how resolution is affected with that. But if you'd like to reach out to me, I can definitely talk offline or do some research and we can figure out what that looks like for your application.
I'll make sure you get everybody's contact information
Thank
and the
you.
questions. Next is a comment, very content-rich presentation. Thank you. And I agree. So here, moving on is, do you offer any service to help us out to choose the right lighting?
Yes, definitely. So we do have some machine vision labs set up throughout the United States. And you can send us samples. We can actually do all the testing for you and tell you exactly what products you would need to solve your application. Or if you'd like to do that yourself, we can definitely, work via Skype or webinar and help you figure out what lighting and lensing, all that you need.
Okay, thank you. Next question here is about drones. So I'll just throw it out here. Any
Sure.
any recommendations for drones for inspecting infrastructure, for example, bridges and dams?
Sure. Wow. That sounds really cool. So probably, well, of course, with a drone, you want something light. I mean, if you'd like to reach out to me, I can definitely recommend to you a couple of our cameras that are very lightweight, high resolution cameras. And I think that's probably the place you'd want to start.
Okay, thank you. Can you comment on the pros and cons of CMOS technology versus standard CMOS?
I'm not too familiar with those two, so that's spinning current. Not exactly sure.
Okay. I think SCMOS, I think it might be scientific cameras. Anyways, next question here. How do you calculate the field of view?
Sure. So there's a bunch of different calculators online that are actually very good. We have one on our website. And basically that's a factor of, how big your part is, how much tolerance that part will have in placement, and then the lens size that you need and how far away your camera is being mounted. And basically, you plug all those factors into a calculator, and it'll tell you what field of view you need or what lens size you need, and things like that.
Okay, thank you. And this refers to the equation that you showed us at the beginning. Can you use the same equation when trying to image with a different wavelength of light, for example, near, mid, or far infrared light?
Yes, you can. And like I said, it's just a starting point. In those cases, you're your other factors such as lighting and things like that are going to be a little different, but that's still a valid starting point for those types of applications.
Okay, thank you. Next question here. What would be the best calibration object for a camera that is supposed to work well over a large DOF?
The best calibration object, I'd have to take a look at that. I'm not exactly sure.
Okay. Next question here. Cameras are presented in megapixels, but lenses seem to be presented only in focal length. For example, 35 millimeter, 55 millimeter, etc. Can you give more detailed advice about matching lens with, for example, a 30 megapixel camera?
Sure. So focal length and the rating of the megapixel on the lens are completely separate specs. Focal length refers to how the light is focused. So a 35 millimeter lens can be low quality, or a 35 millimeter lens can be high quality. It can be rated for 2 megapixel or 50 megapixel. Really, the megapixel rating is based on the quality of the lens. So you can have a very high quality lens of 35 millimeter or low quality. I'm not sure which lenses you're taking a look at, but typically the lens manufacturer will have what it's rated for. It's a separate spec. If you want to take a look at the Baumer website, all our lenses are spec'd for a certain megapixel rating, and that's the rating that you need to match up with the megapixel rating of your camera.
Okay, thank you. This is a question that just asks if you can you address liquid lens regarding heat, damage susceptibility, key applications? So I don't know if that's...
Sure.
No.
Yeah, so liquid lens, we don't have too much familiarity with that. That's something we're developing. We have only worked, our cameras have only typically worked with full-length lenses. I do know that the liquid lenses are more susceptible to, just based on the fact that they're, constantly moving, they're more susceptible to damage and, wear and tear and things like that. But I'm not exactly sure how much more.
Okay, thank you. Okay, I'm going to go for 3 more questions, Daniel, and I will be sending you all of the questions. We got a lot of questions today. So next one here in line is, will depth cameras take over from monocular or stereo pairs?
Sorry, 1 second. I'm having trouble hearing you. Could you say that again?
Sure.
There we go. Now I can hear you.
Will depth cameras take over from monocular or stereo pairs?
I'd have to take a look at that. I'm not too familiar with the trend on those, but I can get back to you on that for sure.
Okay. How does one test various lenses without having to buy them all?
Sure. Well, you can send us the part that you're trying to test, or we can loan lenses, cameras, lighting to you if that's something that you'd want to do. Typically, you can work with a machine vision supplier, and they will help you with that. If you don't want to purchase it, you can of course get loaners and things like that.
Okay, I'm going to go for one last question here, Daniel. How do you calculate the resolution of the camera you need when using a fiber bundle to deliver the image? Would it be the same equation?
Yes, I have never done that, but yes, it would be the same equation.
The same equation that you showed at the beginning.
Correct.
Okay. All right. So at this time, I'm going to conclude the webinar, and I want to thank all of our attendees for joining us today. I want to thank Daniel Olache from Baumer and our sponsor, Midwest Optical Systems. And I do want to remind attendees that if they would like a copy of this presentation to please email me. You will receive my email address in a follow-up note tomorrow. And as I also said previously, I will make sure that Daniel gets a copy of all of your questions and your contact information so he can follow up. Thank you once again, everybody, and thank you, Daniel.